Hi, I'm Daniel and this is my video for the ESA paper titled Sometimes Reliable Spanners of Almost Linear Size. This is joint work with Kevin and Zariel. The graphs that we are working with are geometric, which means that their vertices are located in some d-dimensional Euclidean space and their edges are straight line segments. They are weighted with Euclidean distances. In such a graph, we say that a path between 2 points u and v is a t-path if it has a length at most t times the Euclidean distance of u and v. And we say that such a graph is a t-spanner if it has a t-path between all pairs of its points. This particular example is a spanner with t equals 2 because it has a 2-path between all pairs of its points. Geometric spanners are natural objects, and there are several properties that you can analyze regarding spanners. So one such property is their resistance against vertex failures. This is the one that we are going to investigate. So the setting is the following. We have a geometric spanner and there is an attack on this graph for a set of vertices that fail. We are interested in the spanner properties of the residual graph. So the most natural notion is fault tolerance, which captures this. It has a parameter k, and the k fault tolerance spanner can withstand failures of at most k vertices. We see immediately that such a spanner must have degree at least k plus 1, otherwise there would be a vertex that can be isolated by simply deleting its neighbors. So this means that the size of this graph, so the number of edges that the fault tolerance spanner must have, grows linearly with k. And another disadvantage is that beyond k there is no guarantee. So if more than k vertices fail, we cannot say anything about the graph. So therefore one would choose this parameter k to be big, but then of course the size grows. So in particular, if k would be proportional to n, this would mean that we essentially need to build a complete graph. So this shows us that fault tolerance spanners work perfectly with small sized failures, and if we know that only small sized failures can occur, so then we can choose this parameter k to be something small, for example log n. But if you want to prepare for huge catastrophic failures, then we essentially need a complete graph. So here's a natural question: how to construct such a graph that can survive catastrophic failures while having fewer edges, so not a quadratic. So that's how reliable spanners come into the play. Let me show this notion via the example that I just had in the first slide. So we have this graph here, which is a 2-spanner, and suppose that we have vertex failures. So here's a set of failed vertices, and we see that between the two red vertices we don't have a 2-path anymore. So what do we do here? Well, the trick here is to introduce set B+, the so-called damage set, which is a superset of the failure set B, and we only want to maintain 2 paths for pairs of points that are outside of this damage set. So we don't need this path between the two red ones. And notice that the points that are in the damage set but not in the failed set are not deleted from the graph, so we can still use them as an intermediate vertex to maintain good connections between other points. And last but not least, we want to have some bound on this damage set. So for this we have a parameter theta, and we require that the size of the damage set must be at most 1 plus theta times the number of failures. So this is quite a strong requirement because it only depends on the number of failures and it's independent of the network size. Using this notion we can prepare for huge catastrophic failures as well. For example, if you choose theta to be something small, then suppose half of the vertices fail in the network, then we still have a linear size component that survives the attack, essentially. So let's see the formal definition. So graph G is a theta reliable t-spanner if for any failure set there exists a damage set such that the size of the damage set is small, and for any pair of points outside of this damage set there is a t-path in the residual graph. Okay, so what do we know about reliable spanners? Well, we have both lower and upper bounds. The lower bound says that in order to construct reliable spanners, we need at least n log n edges. The upper bound is almost tight, so it has only a log n to the 6 extra factor. We see here that it's much better than quadratic sized construction for the fault tolerant spanner case. This is already a huge improvement, but with this work our goal was to go even further. So we see this n log n lower bound, but we want to go beyond that, so we want to bypass it somehow. And the way we can do that is to add randomization to our constructions. So that's what we are going to do. And that's how we arrive at sometimes reliable spanners. So here we will consider random graphs, and we say that a random graph G of theta reliable t-spanner in expectation if for any failure set there exists a damage set such that the size of the damage set is small in expectation. So we relax the deterministic bound on the size of the damage set, it only has to hold in expectation. This can be thought as having a deterministic graph and random failure, so that would be a very similar setting. But here we have the randomness in the graph construction, and that's how we incorporate randomness. So let's see the results that we have. We have two constructions for sometimes reliable spanners, one for the 1D case and one for higher dimensional point sets. So in one dimension we were able to construct theta reliable 1 spanners in expectation with the linear number of edges, so that's optimal. We cannot do better, of course, because the graph must be connected. And for the higher dimensional case we were also able to bypass the n log n lower bound, but we have some extra double and triple logarithmic factors, so that's what we meant by the almost linear size in the title. The idea for the 1D construction is essentially a reliable skip list, and for the higher dimensional setting we use a very nice result called locally sensitive orderings along with our one-dimensional construction. So let's see the 1D construction first. First we define a structure on the points. Suppose that the number of vertices is a 2 power, so n is of the form 2 to the k for some positive k. And suppose that we have a full binary tree where the points are located in the leaves of this tree from left to right in increasing order. And then we play an elimination tournament, which means that for each internal node we flip a fair coin to decide whether the left or the right child wins. And the winner occupies the node. So in this way we get a logarithmic number of levels, and that's the structure that we have on the points. Now we can define the edges. We define edges for each level separately, and on level I, if a point P is present in level I, then we simply connect it to the first Li neighbors to the left and the first Li neighbors to the right on this level. Notice that this Li grows with I, so this means that on higher levels a point has more connections, and that also means that these connections are much longer, because in higher levels there are less vertices. So that's the construction. We can easily analyze the number of edges that this graph has, because we know the number of vertices on certain levels, and we also have a bound on the degree of each node in each level. So we can simply sum up and get a geometric sum and linear size. So that's a really simple analysis and construction as well. So let's see how do we find reliable path between pairs of points in the residual graph. Suppose we have P and Q and we want to find one path between those. So what we do is to define the object that we call a stairway. A right stairway of P is a path that goes to the right, and it's not only going to the right, but it's also climbing up in the level structure. So the next node along the path is always present in some higher level than the previous one. And this is what we call a right stairway of P. This stairway must be safe, which means that none of its points should be in the failed set, and we say that the stairway is usable if it's long enough, basically, so it reaches till the end of the graph. So the last vertex along this stairway is connected to all vertices that are to the right of it. And now I think the intuition is quite clear. So if P has a right stairway and Q has a left stairway, which we can define in the same manner as the right stairway, then these two stairways must cross each other at some point. With some care at the point where they cross each other, we can construct a path one path that connects P and Q. Okay, so this means that we can essentially classify points, whether they are good or bad. And a point is good if it has safe and usable stairway to the right and to the left as well. And all other points are bad points. And on the previous slide we saw that between any two good points we do have a one path. So what we need to do is to simply bound the number of bad points. And we want to do this in expectation. So for that we want to compute the probability of a point being bad. And this probability, of course, depends heavily on the actual location of the failures, because the intuition again is that if a point is close to the failure set, so it has many neighbors that are in the fail set, then it's more likely to be a bad point. But on the other hand, if its neighborhood has only a few or doesn't have a failed point at all, then it's more likely to be a good point, because it will have a hub close by, so the point which is present in some high level, and therefore it will have long stairways, essentially. So for this we classify points based on how close they are to the failed set in some suitable sense, bound the probabilities for each of these classes. And by doing the math carefully, we end up with the bound that we want for the expected number of bad points. So that was the one-dimensional construction. Now let me talk a bit about our higher dimensional construction. So here we have a point set in the d-dimensional Euclidean space, and the main tool or the main result that we use for this construction is a result of Chan et al. On locality sensitive ordering. So what does this result say? Well, it says that you only need to maintain a few linear orderings in order to have a nice property, which I will just explain. So for any pair of points, P and Q, you can pick an ordering from this set of orderings such that all points that are between P and Q, according to this order sigma, are either very close to P or they are very close to Q. Let me elaborate a bit on this. There is a parameter xi that this theorem or result has, and the number of orderings depends only on this parameter xi. The radius of the balls that we have around P and Q is xi times the Euclidean distance of P and Q. So these balls have radius relative to the distance of the 2 points. The cardinality of pi, so the number of orderings that we need, only depends on xi, so that's good. It's independent of the number of vertices that we have in V. And we can choose this xi to be something close to 0, practically. So once we have this set pi, no matter how we choose P and Q, we will find an ordering sigma for which this property holds. So that all points that are between P and Q are either in this ball around P or in this ball around Q. Okay, so how do we use this result in our construction? Well, it's very simple. So we compute this set of orderings, and for each of these orders we simply build our one-dimensional construction, and then we take the union. So why is this good? Well, the idea is basically that the reliability is inherited from the 1D construction. So when we want to find a 1 plus epsilon path between 2 points P and Q, then we just go to the appropriate ordering for which this property holds, and then look at the 1D subgraph that we have. So in this 1D subgraph, we have a reliable one path between P and Q. So what does that mean in the original space? Well, if we go back here, this means that starting from P, we have a few jumps here in this small ball around P. Then there is one long range edge from the locality of P to the locality of Q. And then there again we have some short range edges, and then we arrive at Q. So if we do this carefully, I mean by tuning the parameter xi, for example, we end up with the construction that we want. So that's the idea behind the higher dimensional construction. So now let me summarize what we have. We showed the constructions for sometimes reliable spanners, and we had two constructions, one for the 1D case, one for the higher dimensional setting, and in both cases we were able to bypass the analog and lower bound. And for the 1D case we have the optimal size, which is linear, of course, and for the higher dimensional case we have these extra double and triple logarithmic factors. Thank you for watching my video.